we continue with different aspects of equations of the equations of motion, and in this case particularly we are discussing the famous continuity equation, or also known as mass conservation equation. We just derived it from different methods, one by using the control volume and the divergence theorem, and the other one we use by using infinitesimal changes. If we write it in the Cartesian coordinates, this can be written as the divergence theorem. The quantity can be written in this form for a steady equation, and that the divergence of rho times v will be equal to this if we are using rectangular coordinates. However, if we try to convert it to cylindrical coordinates or cylindrical polar coordinates, then the same equation can be written in the form as given below, that is 1 by r times partial derivative with respect to r of ru, the radial component of velocity ur. This is the angular velocity component of velocity, that is we denote by u theta, and this is the normal velocity component in the z direction. The cylindrical coordinates, as you know, are shown in r, theta, z directions. This is a standard format, and actually it is very important. The flow of fluid, if it is taking place in a planar motion, then it's better to use rectangular coordinates. If, let's say, the flow is taking in a cylinder or in a geometry that is similar to cylinder, we try to use cylindrical polar coordinates. And similarly, if sometime we need to require spherical coordinates because of the type of the motion, then we use spherical polar coordinates. So the transformation is done according to the requirement. For the divergence part, we have written this. So the equation that we obtained and that we wrote in this form, if we expand it by using the divergence formula for vector quantities, this will be equivalent to derivative of rho with respect to time as it is, but divergence of rho times v will be equal to d rho by dt plus v times gradient of rho. And remember, gradient of a scalar quantity is a vector. So therefore, a vector sign has been shown here, plus rho times divergence of v. So the expanded form of this is being written here. But this much component in this expanded form is known as material derivative of rho. And remember, the material derivative is when we are taking the changes in the flow that are taking place with the flow. That is known as material derivative. As the material element moves through a flow field, its density changes according to the equation. So capital D rho by dt is indicative of the material derivative of rho, and it is only showing that the density is changing, shown here in the picture as a larger quantity than a smaller quantity, and as the stream is moving, the density may change with the movement of the flow. On the other hand, if the changes in the density of the material element are negligibly small compared to the magnitude of the velocity changes, then the divergence of v as the elements has moved all around, then we take 1 over rho times capital D by dt of rho as approximately equal to 0. So we have taken divergence of V to be a 0, we have kind of ignored it, and the flow is approximated as incompressible. That is, the flow is incompressible when there is no change in density. And as we have said here, if the changes in density are, the changes may be taking place, but they are so small as compared to the changes of the magnitude of the velocity that they can be ignored, and therefore this is approximately equal to 0, or this quantity is approaching 0, and we are left with a quantity divergence of V is equal to 0. The equation of motion, as you can see, then if this part is eliminated, we are left with only divergence of V is equal to 0 that I wrote here. So these are special cases of continuity equation. If there are changes in the density, that is, density is changing with time or with the motion, different conditions prevail, and then we cannot keep this term as 0. We have to keep it, we have to retain it in the equation of motion. But under the condition, and in many cases this is true. For example, if the fluid is water, then we don't expect much change. The water retains its value and its density, and therefore in that case the fluid is incompressible. But if, let's say, the fluid we are considering is not water but gases, then in gases the density is most likely to change. So these are the considerations that we should always keep in mind while applying the continuity equation.